So I'd like to thank the organizers for the invitation to speak here. So my talk will be mostly algebra combinatorial with a little bit of geometry at the end. So let me start with the setup. So we take G to be reductive algebraic group over the complex numbers over C. And we fix a pinning, so a torus inside a Borel inside G. And then if we look at a parabolic inside our group, then the torus fixed points on the smooth projective variety G mod P are isomorphic to the quotient of the Val group of G, quotiented by the Val group corresponding to the parabolic. So for P, a maximal parabolic, so we think of G mod P as a one-step flag variety, often called the Grassmannian. So I would like to think about two types of Grassmannians for the purposes of this talk in the context of Schubert calculus, namely the case where G is GLN or when G is the symplectic group. So let me just set up a little bit of notation for the, well, more specifically the symplectic Grassmannian. So we have SP GER of isotropic K-planes inside 2n-dimensional space, embedding into, so type A Grassmannian, which is K-planes inside 2n space. And we'll like to work with the torus fixed point. So we'll also think about the fixed points of the Grassmannian embedding into GER and the fixed points of the symplectic Grassmannian embedding here. And so for future purposes, let me mention that the Grassmannian fixed points here can be identified with strings which have k0, so binary strings which have k0s and 2n minus k1s. Is that too low? Can people at the back see? No, okay. So this side we can identify with binary strings with k0s and 2n minus k1s. And for the symplectic Grassmannian, we can think of, so again we have zeros and ones. And for historical purposes, I'm going to call the third letter 10. I hope this will not be confusing. So we have n minus k tens and k zeros and ones. So again, strings with those letters. OK, and here I'm really thinking about the rank n torus. OK, so, and let me just tell you what is this inclusion map iota tilde here. So iota tilde of such a string takes it to, so nu bar with tens mapped to ones. Where nu bar means reverse nu and swap 0 and 1. OK. So now that we've set up our Grassmannians, we'd like to think about Schubert classes corresponding to them.
Did you mean the statement about fixed points for the normal Grassmannian or for the?
Which one, sorry?
The number of fixed points, did you mean this for the normal Grassmannian or really for the?
Yes, yes, that's a good point. So the T2n fixed points were going to be the same as the torus fixed points for the torus of the Grassmannian will be the same as the torus fixed points if we use the torus from the symplectic Grassmannian, because we have an element here with distinct eigenvalues. So you're right, this is a technical point that this is in fact equal to GER K 2n T2n. Yeah. But yes, thanks for keeping me honest. So for the Schubert classes, so we're thinking about so S pi being, so the opposite Borel pi, P mod P, so the class of the closure of that. So if we take this collection as pi ranges between among WG mod WP, then these give us, so this freely generate the equivariant cohomology of the partial flag variety as a module over the equivariant cohomology of a point. Okay. So then the classical question relating to Schubert classes is, what are their structure constants? So what are the structural constants here? So namely, if you take S lambda times S mu, and you want to expand it in S nu, what are these C nu lambda mu's? And so these structural constants also appear. So in type A, when we're looking at this Grassmannian, so these are exactly the Littlewood-Richardson coefficients. If we're looking at the tensor product multiplicity of irreducibles for GLK, so GLK irreducibles. Okay, so one way this question was answered was using the combinatorial tool of puzzles. So Littlewood-Richardson coefficients were traditionally studied in terms of tableau, but thinking about the setting of the Schubert classes, so we can also realize these or count these numbers in terms of puzzles. So let me tell you what puzzles are. So for the moment I will restrict my attention to type A. So a puzzle which let's say of size 2n. So we'll think of it as an equilateral triangle labeled with lambda, mu, and nu on the sides, where lambda, mu, and nu are binary strings of the type we considered before. So is a tiling of this triangle with the following pieces. So this is a 2n by 2n by 2n equilateral triangle, and we'll have smaller triangles of size 1, 1, 1, which can have zeros on the boundary, ones. And now there's one extra special triangle which will have 0, 1, and 10. But the 10s will only be allowed in the interior, so not on the boundary for now. And so these were originally found combinatorially, but recent work of Knutson and Zinn-Justin has shown that these are secretly weights for the C3 representation of the quantum loop group for SL3. So you can really think of them as weights for a C3 representation. So we have these three types of triangles. We can also rotate them. And so this is unusual cohomology. And if we want to think about equivariant cohomology, then we also need an extra piece, which looks like a rhombus with the label 0, 1, 0, 1 like this. So this is the so-called equivariant piece, which we use when we're interested in the coefficients in the case of equivariant cohomology. Okay, so now is the time to reveal the other side. I can switch export. So here's an example of such a puzzle. Oops. So let's just focus on the left side of the board first. So this is a spoiler for what's to come. So here's a tiling, I hope the red is readable, of a triangle by such pieces. And so a theorem by Knutson and Tao tells us that counting these triangles gives us precisely the coefficients when we multiply Schubert classes. So
you say type A, so you mean the 10, or this is for type A and type C? Or
so this so far is only for type A.
Okay.
Yes, this rule is only for type A. In fact, I think the purely type C rule is not known in terms of puzzles yet. Yes. So I will talk about how type C comes into the picture a little bit later on and how it mixes with type A. But so far, type A, I really mean GER K2n. And that's what our binary sequences indicate as well. Yes?
So can you explain once again what does this notation 10 stand for?
Oh, yes, this is just a sort of a historical, I mean, the fact that it's a 10 is not really important. It's just sort of a historical artifact. So really, it comes from, so originally it was only found combinatorial, and there was no real good explanation. Only recently, it's been realized that even though we're thinking of one-step flag varieties, we really need to, in order to fill in these puzzles, we really need to think about SL3 rather than SL2. So the interior here somehow has, involves a representation for SL3. Yeah, so these 1, 0, and 10 are really the weights of an SL3 representation. Yeah. So theorem from 2003 by Knutson and Tao tells us that if we, so computing these, the product of the Schubert classes, so the product in H star T of GER K2n is given by, so S lambda times S mu is the sum over nu, where lambda, mu, and nu are all binary sequences of that type. So, and here, so we have another sum of, so a quantity which, due to my physics co-author, we call fugacity of a puzzle where P is a puzzle of type lambda, mu, and nu, S nu. So this is the coefficient which involves counting these puzzles. And let me tell you how to determine the fugacity of a puzzle. So the fugacity of any little triangle with any labels A, B, and C is always 1. And if we are interested in the equivariant piece, so the 0, 1, 1, 0 piece, we look at how it connects to the bottom, and if it's in the ith and jth position, then the equivariant piece has fugacity yi minus yj, which lives inside h star t of a point, which here is just the polynomial ring in y1, up to y2n. So in this example, what we're looking at is S, so 1, 0, 1, 0. So that Schubert class multiplied by the Schubert class 0, 1. Oh, sorry, there should be a 1 here, a 0 rather. So S0, 1, 1, 0. So it's going to have some expansion in terms of classes again, and this puzzle is telling us that the class S1, 0, 1, 0 will appear with a coefficient which will include, so this equivariant piece gives us y1 minus y2. This equivariant piece gives us y3 minus y4. And so all the triangles have fugacity 1, and we take the product over all these fugacities. So we know that this will look like y1 minus y2 times y3 minus y4. And there might be other puzzles with the same boundary. So there might be more to this coefficient here, and there might be also other classes. But this is how you count the puzzles. Any questions so far? OK. And so these are polynomials in equivariant cohomology, but if we're just looking at regular cohomology, we're just literally counting the puzzles. So it's a positive rule for these structure constants. OK, so this is the classical theorem by Knutson and Tao. So let me make one observation about these puzzles now. So we have a certain Grassmannian duality where we can look at the Grassmannian of k-planes in some space V, which is isomorphic to the Grassmannian of dimension V minus k-planes in V dual, where you just take a k-plane to its perp. And so the cohomologies are isomorphic. So we have h star t of the Grassmannian of k-planes in 2n space is isomorphic to h star t of Grassmannian of 2n minus k-planes in 2n space. And under this isomorphism, a Schubert class goes to S lambda bar, where lambda bar here meant as before, reverse the string and switch 0 and 1. And so on this side, counting puzzles of the type lambda, mu, and nu corresponds to, on this side, counting puzzles of the form mu bar, lambda bar, nu bar, which were also obtained by reflecting through the this axis. So taking the dual of this puzzle just meant reflect, so and reverse all the strings. So reverse zeros and ones in the interior as well. So somehow using these puzzles to count the structure constants is equivalent to using these dual puzzles, the dual of the original puzzles, to count structure constants. And so one natural question is, what are self-dual puzzles? So what do they count? So what do self-dual puzzles count? OK, and for the rest of the talk, I will use the simplification that if we have a self-dual puzzle, we can really only worry about half of it. So since it's self-dual, 1/2 determines the whole puzzle. So this is the same as half puzzles. Okay. Any questions, comments?
Why is Paul forget?
That's a good question, and you should ask Paul that. It's something about the property of gas and ideal gas. In this context, I don't know the immediate answer.
It has something to do with some kind of weight, right?
Yes, exactly.
Not just a number, you get like a weight. So if you set the parameter to 1, you get the number back.
Yes, that's a good answer. Thanks.
But it looks like
Yeah. Yes. So, okay, so what do self-dual puzzles count? And so the answer is, which we'll get into in a moment, is that they tell us something about restricting from type A to type C Grassmannians. So they tell us about restrictions from type A to type C. Okay, so let me explain in some more detail precisely what I mean. So at the beginning, I told you about the inclusion of the symplectic Grassmannian into type A Grassmannian. So now let's look at this map in cohomology.
So why do we restrict to C and not B and D?
You can also do B and D. We just haven't worked it out yet, but it should generalize as well fairly easily, I think. So yes.
And do you expect for type B to answer, the answer to be somewhat similar?
Yes, I think so. Later on in the proof, I will write down some matrices like R and K matrices, and we'll just have to modify them. That's where the
RK is as in the N1 circuit.
yes. So hopefully I'll get to that, but I think we'll just need to make some modification for these matrices, which allow us to produce the rule. Okay, so let's talk about cohomology rings. So using the inclusion diagram from before, now we have so the equivariant cohomology of the Grassmannian. So this is the pullback of the inclusion map going to T equivariant cohomology of the symplectic Grassmannian. Oops, sorry, this is 2n. And this maps to T equivariant cohomology of the fixed points. The symplectic Grassmannian of K2n. And so what we're interested in is what happens to Schubert classes under the top map. The way we'll think about it is using the bottom line. So these two maps, G1 and G2. So since we have the torus action on a smooth projective variety, I believe due to Kirwan, these two maps, G1 and G2, are injective. So Gi are injective. So it suffices to work on the level of T fixed points. Okay, and this will be mostly relevant for when I say something about the proof of the theorem I'm about to state. So then our theorem for self-dual puzzles is the following. So, so for every Schubert class in H star T of the Grassmannian of K-planes in 2n, so here lambda is a binary string with this content. If we want to understand what happens when we restrict to the symplectic Grassmannian, then the rule is the following. So here on the symplectic side, as we saw, the Schubert classes are indexed by strings with n minus k tens, and the rest of the k integers are among 0 and 1. And so here the coefficient is, so again, summing over the fugacity of puzzles, where P is a half puzzle, so with size lambda and nu. So it's any filling, any tiling of the half puzzle of this type. So I'll call this coefficient C nu lambda. And the fugacity we obtain in a very similar way. So one difference or one generalization here is that now we are allowing, notice that now we allow tens on the bottom of these puzzles. So here is an example of such a half puzzle. So what this is telling us is that the restriction of the class 1, 1, 0, 1, 0, 1 so has the class 10, 1, 0 in its expansion with a coefficient including so y2 minus y3 and possibly other things. Yes.
Can you close when you get the full picture?
Mm-hmm.
Or do you look at the full picture?
You don't need to. So in fact, because it's a self-dual puzzle, you can obtain the full picture by just, every 1 becomes a 0, and every 0 becomes a 1. So you can just close it. Yeah.
What do you mean by possible other things? What are the other things?
Oh, well, I just mean we could have other fillings.
Okay.
So even if you fix the boundary, there could be some other filling inside. So, and then you could have some other bottom part.
And also on this vertical line.
Mm-hmm. Yes.
Three rhombi there. Do they have to be rhombi or they can be half triangles?
They can be half triangles, yes. So for instance, this is secretly 1, 0, 10. But all of these triangles have fugacity 1, so yeah. Okay, so so this is the theorem. Now let me tell you a little bit about the proof. And so the proof involves some techniques which we'll hope will be useful in other settings of Schubert classes and more general properties of partial flag varieties. So the idea of the proof is, so we're using 2 techniques. One of them is restricting to fixed points, which has been used before as well for looking at properties of Schubert classes and puzzles. And the second one is using techniques from quantum integrable systems. So this was recently used by Knutson and Zinn-Justin to reinterpret the standard puzzle rule for multiplying type A Grassmannian classes, and we're able to apply it in this setting as well for this restriction formula from type A to type C. So let me say a little bit about this. So we have our half puzzles. And what we would like to do, so they have the triangles inside, or rhombi. So what we'd like to do is take a graph dual. Just because it's easier to work with strings than with these rhombi and triangles. So to each rhombus, we'll associate a crossing. To each half rhombus, there'll be a bounce off the wall. And to each triangle, there'll be a trivalent vertex. And to make things even more interesting, I'd like to use different colors for different parts of this graph dual. So in this case, let me see. We'd like to come in with green lines. And when we bounce off the wall, they end up red. And so the graph dual picture will look like this. I hope the color is visible at the back. But so each of the triangles became a trivalent vertex. Each of the rhombi, or two triangles glued, became a crossing. And each of the half rhombus became a bounce off of the wall. And we'd like to also associate spectral parameters, or our equivariant parameters, to these strings. So we'll go from y1 up to yn, and then minus yn up to minus y1. This is related to how the symplectic torus embeds into the GLN torus. So now we have this picture, and would also like to linearize our puzzle labels. So 0, 1, and 10 now we'll think of as vectors spanning a three-dimensional space. So we'll think of C3, red, green, or blue, as being the span of V0, V1, or V10, red, green, or blue. And so we'll think of each of these strings as having attached one of these C3 spaces to it. And all of the strings will be oriented upwards. So in our general setting, so for a half puzzle which has size 2n and n, we'd like to get a map, which I'll call phi, which goes from C3 blue tensor to the n to C3 green tensor to the 2n. And the way we build it is by associating to each crossing an R matrix, to each bounce a K matrix, and to each trivalent vertex a so-called U matrix. So associate. So to each crossing. And I will suppress the colors for now, but the matrices will be indexed by whatever colors the strands are. So we have some R matrix, and let me keep track of the spectral or equivariant parameters. This goes from C3 tensor 2 to C3 tensor 2. We have one of these bounces, which will associate to a K matrix, which also swaps the sign of the spectral parameter. So it goes from C3 to C3. And we also have one of the trivalent vertices corresponds to a U matrix, which goes from C3 to C3 tensor 2. And we want these matrices to satisfy the following axioms. So this was perhaps one of the main parts of this project, is to find matrices which satisfy, so first of all, the Yang-Baxter equation. So namely, Reidemeister 3 for the more topologically inclined, the reflection equation. So this involves R and K matrices. Which looks like this. And two other more mysterious relations. And sorry, I should have mentioned that here, when we're gluing strands locally, this just means composing the map. So this is just a composition of 3R matrices, so the standard tensor calculus. So we also have swapping trivalent vertices. So this looks like, so say we have two of these interlacing Y's, which cross at the bottom. This should correspond to crossing like this. Sorry for the people who are taking notes. But, and finally, one more mysterious equation, which we decided to call K-fusion, again, inspired by physics and, fusion channels. So it looks as follows. So this is an interaction of the K matrix with the U matrix. So this is should equal this. And so this is a bit mysterious, at least to us. So if anyone has seen something like this before, please talk to me afterwards. But OK, so given maps R, K, and U, which satisfy these properties, what we'll end up having is then the C nu lambda. So this coefficient in our theorem is going to be equal to precisely the lambda nu matrix entry of the map phi, where we think of lambda and nu as being denoting tensor products of these. So a string corresponding to a tensor product of the vectors spanning C3. Now, how do we see this?
What's the relation between phi and RK?
Ah, sorry. So phi here. So phi was this map, which was these bounces together with the trivalent vertices at the bottom. Oh. And so once we have these RK and U, phi will be built out of those. Yeah. So what we need is for these maps which make up phi to satisfy these properties. Yes. OK, so.
Sorry, does this mean that when you have these things, the entries of this matrix are counts of puzzles?
Yes. So this matrix entry. So we have the map phi, and when you input lambda and output nu. Oh, sorry, input nu and output lambda, because we're going the other way. That matrix entry gives you the sum of all the puzzles which have boundary nu and lambda. Yeah, so that.
K and U satisfying the conditions, that will be true?
Yes. Yeah. So we do have explicit examples of the matrices which satisfy these conditions. I'm not writing them for time's sake, but any collection of matrices which satisfy this will work. Yeah. And so maybe let me just mention, so this is the first step, translating our puzzles into these scattering diagrams, if you'd like. And then the next step is restricting to fixed points, to torus fixed points. So in order to see that what I claim here is in fact true, so restrict to t fixed points. So what we're interested in is computing, so S lambda restricted to mu. And So the point is that we can also do this using the string diagrams that I described. So let's say in fact, for general G mod P, where lambda and mu are in WG mod WP. Okay, so what we need to do is take shortest length representative for mu. And take a reduced word for that. And then replace each of the elements of this reduced word with either an R matrix or a K matrix. So if we're in the type A Val group, so Si will go to Ri, or I guess S0, the special element in type C, will go to the K matrix. And I should point out that these are the blue R matrices, so there's some technical work about keeping track of the colors. But so this map now will tell us, will give us this restriction to T fixed points. So again, we're building a map out of R and K matrices, so let me just do a quick example. Let's say we're looking at G is equal to SP6, and mu is the string of the form 10, 10, 0. Then a reduced word looks like S2, S3, S1. And so we have the diagram of the following type, with the parameters y1, y2, y3. So this corresponds to, so our matrix, okay, I'll write on this board. So all our strings are oriented up. So this is an R matrix tensored with the identity. And then we have a K matrix with identity squared, and another R matrix. So this goes from C3, 3 tensor copies to itself. So we get this diagram and the corresponding map, and then, so maybe I'll say we get a map psi, which involved the choice for mu. And so this is now a rewording of the Janssen-Zurgel-Billy formula for restriction to T fixed points, so of the AJS-Billy formula. So S lambda restricted to mu is equal to, so the lambda identity on G mod P matrix entry of psi. So we can compute this restriction to T fixed points also using these string diagrams. And this is just the identity string on G mod P. Yes?
Can you say again like S naught, please?
Sorry, S naught? Oh, this is just the special element when we're working with the Val group of type C. So the negation. Oh, sorry. Okay, I should call SN. Okay, thanks. Yeah. Yeah, it's SN. So the one which does the reflection through the wall. Yeah. Okay. Right. So we're able to translate the AGS-Billy formula also in this language. And so then the proof really becomes a play with these scattering diagrams. So then the sketch of the proof of the theorem is the following. So I'll just use boxes and triangles to indicate these diagrams. So let me draw it as follows. So iota tilde of mu, where we put lambda on this end and the identity of the Grassmannian on this end. So this means S lambda restricted to nu. So imagine just putting the scattering diagram, iota star of S lambda. So this was the thing we were interested in, and we restricted to the fixed point nu. And I use this rectangle just to denote the map corresponding to the scattering diagram here. So this is equal to, so now using the properties of the R and K matrices, which are inside here. So the sum of, so we still have a map here together with a half puzzle now. So here we have identity on Spager, lambda mu, and we still have iota tilde of nu. So, sorry, this is all short notation for the scattering diagram maps that are going either as described here or as described in the half puzzles. And so this is equal to, so here we're summing over, let me see, mu in 0 to the k, 1 to the 2n minus k. So again, using the properties of r, k, and u, this is equal to the sum of lambda, nu, and identity on Spager, whereas here we're summing over beta. And this is exactly the left side of the, so by our conventions, this is exactly C lambda nu S nu restricted to, beta restricted to nu, summing over beta, where beta here is a t-fixed point of the symplectic Grassmannian. So we're just using the properties of the string diagram maps to write down this equation. Okay, so let me say a little bit about generalizations for this. Where we are hoping to involve some more geometry in thinking about these puzzles. So, and this is where it's going to be a little bit sketchier and more schematic. So far I was telling you about partial flag varieties and Schubert classes. So we'd like to generalize this to the cotangent bundles of partial flag varieties and Maulik-Okounkov stable classes. So I'll just call them MO classes for short. So the idea is to use Lagrangian correspondences to understand the restriction of these MO classes from type A to type C. So to find the restriction of MO classes. So from now we have so cohomology of the cotangent bundle of the Grassmannian, and we have the torus together with the dilation action on the fiber. So from there to the cotangent bundle of the symplectic Grassmannian. So I'll just write T star Spagar of K2n. Okay.
Combinatorially, you expect some similar kind of formula, but there'll be some additional C star covariant
Yes.
class,
Yes.
some like variable or something.
Yeah, exactly. So as a cohomology, I guess it's not that different because this is just isomorphic to the T star equivariant cohomology of the Grassmannian together with this extra dilation parameter h bar. But yes, so we expect, so some of the upshots of this are to understand get a more geometric understanding of these puzzles. So using these Lagrangian correspondences. And so one of the things I didn't mention about the R matrices are that, so we'll have a more general integrable system here. So the R matrix that we used in this setting was the one coming from the 5-vertex model in statistical mechanics. And using the cotangent Monroe and Maulik-Okounkov classes would allow us to use the more general 6-vertex R matrix, which is, I think, the most general solution of the Yang-Baxter equation in this setting. So it would give us sort of a better geometric understanding together with a more general R matrix. Yes, let me see. Maybe, I'll just stop here, and if there's any questions, I'll